Welcome, ladies and gentlemen. May I have your attention, please? Thank you. Let's go ahead and take a look at our solving equations Bellwork today. So let's solve the following if possible, and if not, explain why. Last activity, we learned how to undo an nth power. We saw we could undo an nth power exponent to solve an equation by raising both sides by the reciprocal exponent, the 1 over nth power. And so if I wanted to solve for x, that is undo a cubing, I could raise both sides to the 1/3 power, the reciprocal of that current exponent, 3. So what we'll do as a means for solving a power equation, x to the n, is raise both sides to the reciprocal power, the 1 over n power. So we're going to purposely raise both sides to the 1/3 power. That's going to be our inverse operation for undoing a power of degree that's higher than 2. So there we go. When we do that, we get x to the 3 times 1/3 is 3/3 is x by itself. That's what we wanted to do. We've got an x alone by raising both sides to the reciprocal exponent. And now we're going to go ahead and ask ourselves the question, what is the cube root, the third root of 64? Right? In order to do that, we have to say what times itself 3 times equals 64. And so everybody go to your half sheet. We've got our brand new half sheet. What times itself 3 times equals 64? That is what cubed, right, equals 64. Be ready, Heather? 4, absolutely. So x equals 4 is a cube root of 64. Okay, we can check this by plugging that into my original. When I plug in 4 in for x, 4 times itself 3 times is 64, so that checks out. So big picture, we need to be able to undo an nth power by raising both sides to the 1 over n power. Okay, that's our inverse operation now. All right, let's go ahead and take a look at our second one. In letter B, x squared equals negative 81. We know that we can undo squaring by taking the positive and negative square root, right? That's equivalent now to raising both sides to the reciprocal exponent, to the 1/2 power. So guys, from now on, the exponent 1/2, right? An exponent of 1/2 means a square root, right? That means a square root. All right, we already have x isolated by itself, so we know then that x would be given by, x squared by itself. So x would be given by the positive and negative square root of whatever is there, right? In this case, whatever was there happened to be negative 81. And so when we go and try to find some number such that when multiplied by itself, that is squared, equals negative 81, what happens? Well, we get negative 9. Will negative 9 work? If I take negative 9 and I square it, do I get negative 81? No, right? What's going on here? Katie?
You can't do a negative number because when it's squared, it becomes
Absolutely, thank you. No real number squared is going to equal that negative 81. And so if I see that my squaring function or even exponent function is isolated on one side, set equal to a negative, right then I know there's going to be no real solution. So I can write that, and that will be my answer. That will be what I boxed like before. So there'll be no real solutions. Okay, let's make a connection to the graphical appearance of my function and the number of real solutions. So everybody, let's look back at our first one, letter A. X cubed equals 64. If I were to go ahead and call the left side of that equation a function, y sub 1, and enter in my grapher, what would x cubed look like? So go ahead and tell the class, is that going to be a bowl shape or is that going to be a disco? What would y equals x cubed look like? Taylor?
a disco.
A disco. And so we're dealing with the situation where my power function here on the left, x cubed, looks like our odd cubing function, right? That's our odd cubing function. And it's set equal to a positive constant, 64. If we entered y sub 2 equals 64 in my grapher, that would just be a horizontal line that's positive, so somewhere up there in the top quadrants. What's the number of intersections of those two graphs? What's the number of intersection points? Luke?
1.
1. How many real solutions are there? 1, and there it is. We found it. Okay, let's go ahead and take a look at number 1b. X squared equals negative 1. In my original power function, y equals x squared, is that going to be a bowl shape or a disco? Margot?
Bowl.
A bowl shape, right? Total bowl shape. And so if I were to consider its graph, that would be like this blue parabola, right? Like this blue parabola. And set equal to a negative constant, in this case, negative 81. That would be somewhere down here in these lower quadrants. What's the number of intersection points in these two graphs? Casey?
0.
0. How many real solutions are there? 0. And so the graphical number of intersections corresponds exactly to the number of real solutions. If there's no intersections, then there's no real solution. If there's one intersection, then there's one real solution. Let's keep on keeping on. So if negative 2x to the fourth equals negative 32, oh, wait a minute. Can I say right now that there's no real solutions? Because we have an even exponent, right? An even exponent and a negative number. Does that mean there's no real solutions?
No.
No, because we're not isolated yet. We don't have a power function alone on one side. So before we can tell, we need to make sure that we have isolated that power function. My best first step to solve would be divide both sides by negative 2. And when I do so, I get my power function alone. I get x to the fourth equals positive 16. So now is my exponent even or odd? Brady?
Even.
Even, right? And so is my even exponent set equal to a positive or negative number? Adam? It's set equal to a positive number. And so is this a situation where I could have one solution, two solutions, or no solutions? All right, is this going to be a one solution, two solution, or no solution based on what we know about our graphical behavior? Olivia?
2 solutions.
Two solutions, absolutely. This is an even power function. We know that that's total bullshit, right? It's similar to a parabola. X to the fourth is not a parabola, but it's a same behavior, like a bowl shape. And if I set that equal to a positive constant like 16, then I have to be on the lookout for not one, but two real solutions because there's two intersections on my graph. All right, let's go ahead and find them. How do I undo a fourth power, right? How do I undo a fourth power? What do I do procedurally? Carson?
16 to the 1/4.
Absolutely. We'll go ahead and raise both sides to the reciprocal exponent. And so I'll go ahead and raise both sides to the 1/4 power. Okay? That's how I undo an exponent of 4. I raise both sides to the 1/4, the reciprocal exponent. And when I do that, it's asking me the question, what's the fourth root of 16? What multiplied by itself 4 times equals 16? Everybody go to your half sheet. Everybody find what to the fourth power equals 16. Get ready, I'm calling on you. Right, what multiplied by itself 4 times equals 16? Caitlin T?
2.
2, absolutely. So the fourth root of 16 is 2. So x equals 2. Awesome. Is that it? No. What other number multiplied by itself 4 times? Barrett? Absolutely. Good job. And so because we were undoing an even integer exponent, we must consider 2 solutions, even though the fourth root of 16 is just 2. We must purposely add the other one, negative 2, because we've got an even power function set equal to a positive number, and that means we could add 2 real solutions because we have 2 points of intersection. So guess what? You have to add the other one. You have to add the other one on your own. You could write plus or minus if you wanted to. Right? When I write them separately, that drives home the fact that there's 2 separate ones, and there they are circled in green. Awesome. What questions do you have about letter C? That's great. All right, let's put it all together now and do some algebraic solving, where my first step is to raise to the reciprocal, and then I have after the fact. And so let's go ahead and see if we can't solve this. If I did my forward steps, I'd plug in something for x and subtract 7, and then raise it to the fourth. So when I undo, right, I need to undo that exponent of the fourth first. I'm going to raise both sides to the 1/4 as my first step, and then I'm going to add 7 last. And so we've got 2 steps for our inverse operations. Let's go ahead and try that. So I'm going to take my x minus 7 to the fourth, and I'm going to undo my exponent first so that I can get at that quantity inside. Ready? I'm going to raise both sides to the 1/4. The reciprocal exponent, just like we did in letter C. When I do that, I get rid of the exponent and get my quantity, x minus 7, right, by itself. I'm ready to solve for that x now. Meanwhile, back at the hacienda, I need to consider the fourth root of 256. Go to your half sheet. Everybody find what number multiplied by itself 4 times equals 256. Be ready. Everybody find it. What number multiplied by itself 4 times equals 256? Ben C?
4.
4. So the fourth root of 256 is 4. But was my original exponent, my original integer exponent, even or odd? Heather? Even. So if my even power function is set equal to a positive number, how many solutions could we have, Cody? 2, which means that even though the fourth root of 256 is positive 4, we must purposely add the negative 4 to the other option, so that we'll have, you guessed it, two paths that you can go by, but in the long run, right, there's going to be two answers here. So x minus 7 equals positive 4, or x minus 7 equals negative 4. Now we can finish it out by adding 7 to both sides. It looks like x equals 4 plus 7 is 11, or x equals negative 4 plus 7 is positive 3. Let's go ahead and check that in my original. So I'm going to go ahead and take 3 and put it in my original. 3 in for x. 3 minus 4 is negative 4. Negative 4 quantity to the fourth would be negative 4 times negative 4 times negative 4 times negative 4 is 256. So we have found our solutions, and there are two of them. Again, graphically, it'll look just like that picture. Even power, right? Even power set equal to. Now, this one will be shifted over, but it's going to be crossing a positive constant twice. This one will be shifted over. It'll basically look like this, right? It's going to be shifted over, and we'll learn that later, but it's still going to cross two different times. Pretty sweet. What questions do you guys have about today's Bellwork?
No questions.
Awesome. Let's go ahead and take care of our homework check then. At this time, I ask that you go ahead and make sure that your name first and last, 1A, number 4 are clearly labeled. This was a shorter assignment, so that was kind of nice. If you showed me your 7 and 7/8 reading questions, then you're eligible for a 5th point Infinite Campus. In pencil, go ahead and give yourself an Infinite Campus score now based on the number that you completed out of 13. Divide, enter, multiply by 4. Reading questions, if you did one of them, plus a half. If you did both of them, plus 1. And then box your Infinite Campus score around to the nearest half point, 0 to 5. What questions do you have about your Infinite Campus score today? Great, and pencils down, please, ladies and gentlemen. And now let's go ahead and check for accuracy using our grading pens. I think I got them all on one page. You know, all on one page?
Yeah.
Awesome. It's like some of you got them all on one page too. That's a nice change. That's all of them. So if you're finishing up, give yourself an accuracy fraction on how many you did, about how many did you get correct. In pen, circle it. Make sure your Infinite Campus score is box, pencil nice and big on top. Final check that your name first and last, 1A. The numbers 4 are clearly labeled, then pass from the back to the front, please. Front rows, make sure they're facing the same direction. I appreciate your help with that. And then we can get your quizzes back to you so you can see exactly how you did. I'm going to go ahead and pause the recording now for our quiz discussion, and then we'll resume when we come back together after your quiz. Okay, ladies and gentlemen, so let's go ahead and take a look then at our objectives for the day. We're going to, again, simplify expressions involving powers and exponents, but today we're going to add fractional exponents, that is, exponents that are a fractional exponent, and we're going to see exactly how we can evaluate those expressions exactly in non-calculator with the use of our powers half sheet. So we'll need our powers half sheet and we'll need our green sheet. Everybody with our green sheet, let's go ahead and add our definition for our fractional exponent rule. Everyone. In our green sheet, this is the one that we skipped at the bottom of page 2. So we're going to define x to the 1 over n is defined to be the nth root of x. Bless you. So x to the 1 over n will define to be the nth root of x. And we did that in our activity last class. X to the 1/4 power will be defined as the 4th root of x. 32 to the 1/5 power will be defined to be the 5th root of 32, and so on and so forth. The second bullet says that b is the nth root of x if and only if b to the n equals x. And this was your number 6 stamp in your activity from last time. Right? B is the nth root of x if and only if I multiply b by itself n times, the result is x. So for our examples, 49 to the 1/2, that's defined to be the 2nd root of x, or more familiarly, the square root of x. In this case, the square root of 49. So the square root of 49 is 7. And that's a single number because there's no plus and minus here. We did not create the plus and minus radical as a means of solving an equation the way we did in our Bellwork. So this is just a single value, and it's 7. The 4th root of 16, there's no plus and minus here. This is just a single number. And we can do this with our half sheet. Everybody find what multiplied by itself 4 times equals 16. That's the 4th root of 16. Look at your half sheet and tell the class when I call on you. Mark? 2. And so the 4th root of 16 is 2. And that's not plus or minus unless we created the 4th root to undo a 4th power, right? Like in the Bellwork. So this is just a single value if you're already given the root and you're evaluating. Does that make sense? Awesome. So we're going to go ahead and first evaluate. What's that?
Are we done with this thing?
We're done with the green sheet for now. We're now going to go back to our note sheet and evaluate power expressions that include rational exponents. That just means an exponent that's a fraction. Jackson, do you have your half sheet? Awesome. You're going to need that. Great. So we'll say, for any non-negative real number x and positive integers m and n, sorry, some throwback tracks, Slim Shady. May I have your attention, please? Would the real Slim Shady please stand up? So let's go ahead and take a look at our rational exponents. X to the m over n is going to be defined 2 different ways. We could purposely choose to apply the denominator of my exponent as an nth root first and then raise to the nth power second. Or we could also take my base and raise it to the nth power before finding the nth root. This one is going to be the most useful for us when we're evaluating non-calculator, because we apply the nth root first, making a smaller number. The nth root, right? The nth root of a quantity is going to be a smaller number, and then raising to the nth power second will be easier to do without a calculator and exactly using my half sheet. Let's go ahead and see what this is going to look like for us. So we'll go ahead and evaluate 25 to the 3/2, and the way we'll do it is by purposely choosing to apply my denominator as a nth root first, to chunk it down to a smaller value, and then I'll raise that to my numerator exponent second. Let's go ahead and take a look at our page recording. So first we're going to apply that denominator as the 1/2 power to my base. So 25 to the 1/2. What's that? Well, that's the square root of 25, which is 5. And then we'll raise to that numerator exponent second. So we'll raise that to the 3rd power. Go to your half sheet. 5 to the 3rd is 125. There it is. So we go ahead and purposely choose to apply my denominator as an nth root first for my base. That'll chunk it down to a smaller number. Take that intermediate result and raise that to the numerator exponent second. We're going to go ahead and watch that again. So here we go. 25 to the 3/2. We're first going to make that 25 to the 1/2 and then cube it second. So look, we rewrote that as 25 to the 1/2. The fractional exponent, we'll do the denominator as an nth root first. What's the square root of 25? Oh, that's 5. And then we'll raise that to the numerator exponent second. So my second step will be raising it to the numerator exponent, and 5 cubed is 125. So in this way, it's like a 2-step process, kind of like our composition of functions. We do the denominator as an nth root first, get an intermediate value, and then raise that to the numerator exponent second. Let's go ahead and try another. But first, we want to make sure you're comfortable with your roots. And so ready? Everybody find your half sheet. Everybody get your half sheet. We're going to practice identifying. We're going to practice identifying nth roots of different things without a calculator. So I'm going to go ahead and play the game too. Let's see. What is the 4th root of 2,401? Everybody find it. What's the 4th root of 2,401? Jackson. 7 is correct because 7 to the 4th power equals 2,401. Everybody get it? Next up. What is the cube root of 729? What is the cube root of 729? Get ready. Carson, you.
9.
9. How come?
Because 9.
Absolutely. And so in this way we can use our half sheet to evaluate power expressions and nth roots, right, without a calculator. That's pretty sweet. All right, let's go ahead and do a couple of these together. I picked out highlighted ones, right, that all the teachers are going to do regardless of which teacher you have or which day you have, so that we have kind of a common base. Everybody, let's take a look at number 1. To evaluate an expression, a power expression with a rational exponent, we choose to apply my denominator of the rational exponent as an nth root first. So I'll rewrite this as 27 to the 1/3, and then raise it to my numerator exponent second. So we rewrote our 27 to the 4/3 as 27 to the 1/3, and then raised to the 4th power. Everybody see that? We do our denominator exponent first as an nth root. Now I'll go ahead and look at my half sheet and evaluate my inside power. What's the cube root of 27? Well, everybody find it. What cubed is 27? Go ahead and tell the class when I call on you. Logan? 3. And so my 27 to the 1/3 is 3. And I still need to raise that to the 4th power. So I go to my half sheet and I say 3 to the 4th equals what? And then tell the class when I call on you. So what's 3 to the 4th? Aaron?
81.
81. Guess what? 27 to the 4/3 power equals 81. It's that easy. So we apply our denominator exponent, right? Our denominator of our rational exponent is an nth root first, and then we take that intermediate value and raise it to the numerator exponent second. Everybody, let's do number 5. 100 to the 3/2. Well, I'll rewrite that as 100 to the 1/2, and then raised to the numerator exponent is to the 3rd. So we work from the inside out. Let's go ahead and evaluate 100 to the 1/2. That's asking for the square root of 100. Go ahead and tell the class what that is when I call on you. Margo?
10.
10. So my inside root is 10, and then I still need to cube that. I still need to raise to the numerator exponent that cubing. And 10 cubed is, everybody find it? Barrett? 1,000, absolutely. So guess what? 100 to the 3/2 power equals 1,000. That's it. We can even do it with fractions, when my base is a fraction. We know from our exponent rules that if I have a quotient, right, a fraction inside parentheses raised to an exponent, that both top and bottom get raised to that exponent. And so let's go ahead and see if we can't work this one out. First, I'm going to apply my denominator exponent as an nth root first to my base. So I'll do 64/9 to the 1/2. And then all that's going to be raised to my numerator exponent second. So my numerator exponent is 3. Let's go ahead and work from the inside out. 64/9 to the 1/2 is asking for the square root of 64/9. Does my square root apply to the top number, 64, or to the bottom number, given that there's parentheses? Both. And so let's do the square root of 64. Everybody find it? The square root of 64. Braden?
8.
Thank you. The square root of 9. Right? The square root of 9. Eric? Good. So we've done 64/9 to the 1/2 power, and we got 8/3. Now we still need to raise that to my numerator exponent. My numerator exponent was 3 from the original. So now I'll go ahead and cube, right? I'll cube my base. In a quotient, in my quotient cubed, who gets cubed? The top number or the bottom number? Both. Let's do it. Everybody find 8 cubed. Be ready. Get your half sheet. What's 8 cubed? Dakota? 512. Thank you. Over. What's 3 cubed? Everybody find it. Marina? 27. Guess what? 64/9 to the 3/2 power is 512/27. And we did it without a calculator and exactly. That's pretty sweet. What questions do you have about our first set? Okay, let's go ahead and try some more then. We're gonna do number 4 and number 10. So, number 4 is 1 to the 7/8. Well, it turns out that 1 raised to any, right, raised to any exponent, then any rational exponent is just going to be itself. The 8th root of 1 is 1, because 1 multiplied by itself 8 times equals 1, and then 1 multiplied by itself 7 times is still 1. And so that's a neat little thing. That's just going to equal 1. I want to do number 6 also. I want to do number 6. Let's do 36 to the 5 halves. Let's do 36 to the 5 halves. And so 36 to the 5 halves would be 36 to the 1 half, and then all raised to the 5th. Let's try that. So we purposely choose to apply the denominator exponent as an nth root first. The denominator of my exponent was 2, so I'm going to find the square root of 36 first and take that intermediate result and raise it to the 5th. So what's the square root of 36? Be ready? Brady? 6, thank you. I still need to raise that to the 5th. Find your 6 to the 5th on your half sheet. And what's that? Olivia B?
7,776.
So 7,776. That is 36 to the 5 halves. Nice job. Let's do number 10. That looks like a pretty crazy problem. Well, remember, there's parentheses here. And so we know that this exponent, 2/3, only applies to what's right next to it. This 2/3 does not apply to the 2/5 in front, because that multiplication, right, is lower down on the totem pole, the hierarchy in order of operations and exponents. So I'm going to leave this 2/5 just chilling. That 2/5 is still going to be there. But I'm going to now take my 8 1/25 and raise it to my denominator exponent as an nth root first. So I'm going to do 8 1/25 to the 1/3, and then raise that to the 2nd power, the numerator exponent last. So we're going to do 8 1/25. We're going to do that to the 1/3 first, get an intermediate result in green, and then we're going to raise that to the numerator exponent 2 last. Let's try it. Ready? Go. 8 1/25 says the cube root of 8. Everybody find it. What's the cube root of 8?
2.
Hang on. Will. 2 over, what's the cube root of 125? Get ready. JP.
5.
5, good. So we've done our green. 8 1/25 to the 1/3. There it is. There's the cube root of 8 1/25. We still need to raise that to the 2nd power, and we still need to multiply by my 2/5 in front. We haven't done anything with that. So we still need to go 2/5 times 2/5 squared is 4 25ths. So it looks like we get 2 times 4 is 8, and 5 times 25 is 125. So we get 8 1/25 again. Interesting. What questions do you have about our first practice slide? And let's keep the party going. We can also use our calculator to evaluate expression. And so for these, we just want to make sure we're using exponents. We just want to make sure we're using exponents. And our 2/3 is all up in the exponent. So let's just do 13. That would be 1,500. Everybody on your calculator, 1,500 to the parentheses 2/3. And it'll just be some decimal. Remember, we can show the reader that irrational number goes on forever and ever by keeping 3 places and then doing ... And so I would write my answer to number 13 as 131.037 ... By putting the ... after 3 decimal places, that lets the reader know that that goes on forever. Go ahead and tell the class what 0.637 to the 3/4 is. Watch your parentheses. So what's 0.637 to the 3/4? Go ahead and tell the class when I call on you. Brady?
0.713 ...
Awesome. Good job with the ... We do 3 places and then a ... to let the reader know that goes on forever as a decimal approximation. Good job, you guys. We'll skip 16. we're good with the calculator. Let's go back to non-calculator. We can even evaluate expressions or simplify expressions rather when we have a fractional exponent using our same exponent rules that we use with integer exponents. So when I raise a power to a power, what's my shortcut operation with the exponents? Multiplication. So we'll simply take r to the 5/8 times 3 over 1 and get r to the 5 times 3 is 15 over 8 times 1 is 8, and I get r to the 15/8. That's it. It's that easy. If I take a product and raise it to an exponent, which power gets raised to the 3/4? The u power or the v power? They both do because they were a product inside of parentheses. So I'll take u to the 2/3 raised to the 3/4 and get u to the 2/3 times 3/4. That would be u to the 6/12 times. Now I'll do my v power. We multiply exponents when I raise to a power, so I get v to the 2/9 times 3/4 is 6/36. And in a final step, we'll go ahead and reduce our exponents. U to the 6/12 is the same as u to the 1/2. V to the 6/36 is the same as v to the 1/6. And we're done. So we've raised a power to a power by multiplying exponents and then reduced our exponents to simplest form. What questions do you guys have about 21? Let's take a look at 23. In 23, that is a product. The y power is not the only one that gets raised to the 5/6. So does the 64. That 64 is in parentheses, isn't it? So the 64 also gets raised to the 5/6. Let's go ahead and see what that looks like. So we'd have 64 to the 5/6 times y to the, and again, we'll multiply exponents. 3 times 5 is 15 over 1 times 6 is 6. So my first step is to purposefully apply my exponent outside of the parentheses to each factor in the product inside. Now we'll go ahead and handle these separately. So let's go ahead and tackle this 64 to the 5/6, and let's do it without a calculator. So how do I do that? Easy. I choose to apply my denominator of the rational exponent as an nth root first. So I'm going to do 64 to the 1/6 first, and then raise it to the numerator exponent, the 5 second. Times, and I'll reduce my 15/6 by dividing out a greatest common factor of 3, and I get y to the 5/2. This y power is not going to reduce at all, so it'll still be in my answer. But this 64 to the 1/6 will. This is asking for the 6th root of 64. Everybody find it. Go to your half sheet. What's the 6th root of 64? And tell the class line colony. What's the 6th root of 64? Barrett? 2. Good job. Thank you. So this equals 2 to the 5th times y to the 5/2. And we're almost there, guys. We just need to do 2 to the 5th. Everybody find it. Go to your half sheet. Everybody find it. What's 2 to the 5th? Olivia B?
32.
32. Thank you. So my final answer is 32y to the 5/2. Nice job, you guys. That's perfect. We'll do one more set with variables. M to the 3/8 all to the 4th. I'll purposefully apply my power of a power property, which means multiply exponents. So this is m to the 3 times 4 is 12/8. And then I'll reduce my fractional exponent and get m to the 12/8. I'll divide out a greatest common factor of 4 and get 3/2. That's it. K to the 4/5 all to the 5/4 equals k to the 20/20 is k to the 1st is k. That's pretty sweet. And lastly, 24, we'll need space for that. So I'm going to go ahead and work to the left again. In order to evaluate this product raised to an exponent, I'm going to go ahead and apply that outside exponent to both factors in my product. So 16 gets raised to the 3/4, and e to the 8/15 gets raised to the 3/4. To do that, I'll multiply exponents. 8 times 3 is 24 over 15 times 4 is 60. And now I'll go ahead and do some simplifying. I know 16 to the 3/4 is the same as 16 to the 1/4, all cubed. See how we choose to apply the denominator as an nth root first, and then raise it to the numerator exponent? Then that's still times e to the, where I'll reduce my exponent, 24/60. Looks like they both share a greatest common factor of 12. Is that right? 12. So this is e to the 2/5. Right? Isn't 60 divided by 12 5? So that black e to the 2/5 power will remain in my answer. It's fully simplified, but we've got some work to do over here. Everybody find it. Everybody find the 4th root of 16. What's the 4th root of 16? Be ready. Luke? 2. Good. We still need the cubed. E to the 2/5. And our last step, what's 2 cubed? What's 2 cubed? Andrew?
4.
8. Good. 8 to the 8e to the 2/5. Good. And we'll box that bad boy. Awesome. What questions do you have about our rational exponent? Okay. Then we also need to be able to solve equations, so I made a little bit extra space compared to yours. Recall from our activity last class that we can solve power equations by undoing an exponent. In our Bellwork, we undid a 4th power by raising both sides to the reciprocal exponent, 1/4. How do you think we're going to undo a 3/2 power? I mean, if we were going to undo a 3/2 power, what would we have to do to both sides? Margot?
Put it to the power of 2/3.
Absolutely. We'll purposely raise both sides to the reciprocal exponent, and that'll undo a 3/2 power if I raise both sides to a 2/3 power. So let's everybody do that. To the 2/3, to the 2/3. That means that n equals 27 to the 2/3. We can evaluate that exactly without a calculator. How do we do that? Easy cheesy. We purposely choose to apply the denominator of my rational exponent as an nth root first, that is 27 to the 1/3, and then raise it to my numerator exponent to second. So we get n equals the cube root of 27. Everybody find it? What's the cube root of 27? Heather? 3, thank you, and I still need to square it. For my final answer, I get n equals 9. For fractional exponents, we're only going to include positive base solutions n, and so I only have a single solution, n equals 9. All right, before I can raise both sides to the reciprocal exponent, though, I must isolate the power. So just like in number C for our Bellwork, we had to do inverse operations before we could raise the reciprocal exponent. So too in 27, do we have to isolate the power. So my best first step is not raise to the reciprocal exponent. My best first step is to instead undo that multiplication. So we must isolate the power first. So we're going to divide both sides by 2 first and get g to the 2/3 equals 49. Now we're going to solve. So how do I undo a 2/3 power? Right? How do I undo a 2/3 power? Taylor?
Do the reciprocal.
Good. We'll raise both sides to the 3/2 power. That undoes the 2/3 power. So I get g by itself, and that equals 49 to the 3/2. What's that? Well, it's 49 to the 1/2, and then all cubed. So g must equal, what's 49 to the 1/2? Right? What's 49 to the 1/2? Everybody find that. Tyler?
7.
7, thank you. And I still need to cube it. So my final answer is g equals 7 cubed, and that's on my half sheet too. What's 7 cubed? Andrew?
343.
Good. 343. Awesome work. We're only going to allow positive base b's, so this is the only result and only solution. Now let's look at number 29. In 29, there's an integer even exponent. Is that even exponent power function set equal to a positive or negative number? Katie?
Positive.
Positive. So how many solutions could this have? Katie?
Wait, well, since we're only doing positive, would it just be one or?
That's a great question. If we have a fractional exponent, then we're only allowing positive bases. But if we have a integer exponent, then it's just like Bellwork. So how many can we have? Two, absolutely. So 29 has two solutions versus 25 and 27 only have one solution, right? How come? Because my even exponent was an integer, m to the second power, and now we're talking our bowl shape, okay? So this has two solutions. And how I get them? Easy cheesy. They're given by the positive and negative square root of 0.64. Sometimes this will reduce, sometimes it won't. It looks like it does this time. I get m equals 0.8 and m equals negative 0.8. So two separate solutions. Good job. Great. Remember, we're only raising to the reciprocal exponent when we're solving, when we're undoing an exponent. If we're evaluating our expressions, right, then we're not changing our exponents. We will change our base, though, in the next section. So let's see how that is going to work out. So the second section builds on the first. That's where we add negatives to our exponents. And so a negative exponent doesn't mean negative answer. It just means reciprocal. This is going to be much like the first half of our discussion today, with the addition of having to flip my base, because the negative exponent refers to reciprocal of the base. Doesn't mean negative answer, it means it means reciprocal. So here we go. If I were to evaluate 27 to the negative 2/3, I'll first rewrite that as 1 over 27 to the positive 2/3. So negative exponent, we hop the line and change the sign on the exponent. That is, we take the reciprocal of the base and rewrite to the positive exponent. So those are equivalent. Next, we'll purposely choose to apply my denominator of my rational exponent as an nth root first. So we'll do 27 to the 1/3 power. On my half sheet, we see that that is 3. And I'll raise that base 3 to my numerator exponent second. So 3 squared is 9. My final answer is 1/9. I'll go ahead and go guide jar on that so that you can see it in the back. Once again, 27 to the negative 2/3 is 1 over 27 to the positive 2/3. Then we apply my denominator as an nth root first. Raise to my numerator exponent second. Work from the inside out, and I get 1/9. And we're going to do several of these together. Let's go ahead and try some together. So 25 to the negative 3/2. Everybody, let's do this together. 25 to the negative 3/2. The first thing we'll do is rewrite this as a reciprocal. That is, hop the line and change the sign. So 25 to the negative 3/2 is the same as 1 over 25 to the positive 3/2. Everybody write it. So we flip the base and rewrite with the positive exponent. Now I'll purposely choose to apply my denominator of my rational exponent as an nth root first. That is to say, I'll evaluate 25 to the 1/2 first, and then raise it to my numerator exponent 3 second. So let's work from the inside out. I need the square root of 25, so that equals 1 over 5. Oh, you're doing it right. See that? We did the square root first. Now I raise that to my numerator exponent second, just like we did the first half of our discussion. Go ahead and find it. What is 5 cubed? Go ahead and so what is 5 cubed? Cody?
125.
Good, thank you. So my final answer is 1. Oh, ask we have it. 1/125. Good, thank you. Let's try another. Negative exponent doesn't mean negative answer, it means reciprocal. So my first step is to rewrite with positive exponents. Here we go. 4/9 to the negative 5/2 is the same as 9/4 to the positive 5/2. So notice how we flip the base, we don't flip the exponent. We apply the negative exponent to flip the base. When we change the sign of the exponent, we don't flip the exponent. So I see that? So flip the base and rewrite to the positive exponent. Now we'll go ahead and apply my denominator of my exponent first as an nth root. Here we go. That's 9/4 to the 1/2 power, and then all raised to the numerator exponent second. That is the 5th power. Do I see that? We apply my denominator of my rational exponent first as an nth root, get an intermediate result, and then raise that to the positive 5th power. So let's work from the inside out. 9/4 is a quotient raised to an exponent, both top and bottom get it. So we need the square root of 9 over the square root of 4. Everybody find it. What's the square root of 9? The square root of 9. Mark?
3.
Thank you. What's the square root of 4? The square root of 4. Adam? 2. So far we've evaluated my square root of 9/4 is 3/2, and now we raise to the numerator exponent last. Who gets raised to the 5th power? The top or the bottom? Go. Let's do it. 3 to the 5th, everybody find it? What's 3 to the 5th from your sheet? Eric?
243.
243 over, what's 2 to the 5th from your sheet? Marina? Awesome. Way to go, you guys. We just handled our first quotient to a negative rational exponent. Way to go. All right, let's go ahead and do some evaluating in our head. That means no calculator, but we can use our half sheet. So here we go. Number 1, 125 to the negative 4/3. Let's try it. That's the same as 1 over 125 to the positive 4/3. So we flip the base and rewrite with the positive exponent. That's the same as 1 over 125 to the 1/3, and then raised to the numerator exponent, the 4th power second. So to do that, we have to find the cube root of 125. So that's 1 over the cube root of 125. Everybody go to your sheet. What's the cube root of 125? Be ready to share with the class when I call on you. Everybody find it. What's the cube root of 125? Olivia H? Good, 5. And so the cube root of 125 is 5, and then we still need to raise that to the 4th power second. So my final answer is 1 over 5 to the 4th. What's 5 to the 4th from your sheet? Will?
625.
Awesome. So my final answer is 1/625. Good work. Let's do number 3. Here we go. Number 3. 64 to the negative 4/3 is the same as 1 over 64 to the positive 4/3. So we'll make a reciprocal first. Then we'll apply my denominator of my rational exponent as a nth root. So 1 over 64 to the 1/3. And then lastly to the 4th. We got to get the cube root of 64, guys, to do the inside parentheses. So what's the cube root of 64? The cube root of 64, Braden?
4.
Good. So 1 over 4 to the 4th. And lastly, what's 4 to the 4th? All right, what's 4 to the 4th? Barrett? 256. So my final answer is 1 over 256. Nice job. All right, let's do 7. So 7, 25/49 to the negative 3/2 is the same as 49/25 to the positive 3/2. See that? We take the reciprocal of the base and rewrite with the positive exponent. That is top the line and change the sign. Next, we'll purposely apply my denominator of my rational exponent as an nth root first. So I do 49/25 to the 1/2, and then all to the third power. So I do 49/25 to the 1/2 power. That's the square root of 49/25. So the square root of 49, 7, over the square root of 25, 5. And now I evaluate 7/5 to the third power. Get ready. Everybody find 7 cubed? All right, what's 7 cubed? Dakota? 343, good. Over. And what's 5 cubed? Carson S? Awesome, thank you. Good job. So we've got 343, 1/25. Woo! I'll tell you what. Serious business. We're, in the interest of time, going to skip number 11, but please know that the negative exponent only applies to the 16. That 4 would still be chilling out front, okay, if we were to do that. But in the interest of time, we're going to skip that. All right, let's go ahead and do a couple more. I want everybody to do number 6 then with your partner. So you're going to try number 6 on your own with your partner. You can talk it out and then we're going to share. Guys, let's take a look at number 6. And so we first rewrite 81 to the negative 3/4 as 1 over 81 to the positive 3/4. Then we applied my denominator exponent as a 4th root first. The 4th root of 81, I went to my half sheet, and I saw that 3 to the 4th is 81. So the 4th root of 81 is 3, and then I cube it last. The numerator exponent was 3. 3 cubed is 27. Raise your hand if you had 127. Who had 127? Great work, you guys. That's awesome. What questions do you have about number 6? Okay, let's go ahead and do number 8 then. Number 8. Go ahead and flip the base, rewrite as the positive, and apply, and be ready to share a response. So you can check with your partner. Let's go ahead and do number 8.
27. So I would get 4 over 16.
Yes, top. Right. Okay, first step. 127 to the negative 1/3 is the same as 27 over 1 to the positive 1/3. So I get 27 to the positive 1/3, and that is a one-stepper. 27 to the 1/3 is the cube root of 27. So I go to my half sheet and I say, what cubed is 27? And I find 3. Raise your hand if you had 3 for number 8. 3? Yes, you guys are doing awesomely. Great job. Okay, we'll go ahead and skip 14 again in the interest of time, and we'll do some with variables, and then we'll have our closure. So we've got one more practice slide. We're going to go ahead and do some with variables to make sure we're comfortable handling variable expressions, and then we'll have our closure slide. So here we go. I handle numerical factors separately from powers, and so my negative 15 over 5 could reduce as negative 3, right? So I can reduce that first as negative 3. Then I'll do x to the 7th over x to the negative 10. I have a quotient of exponents. I can subtract top exponent minus bottom exponent. X to the 7th minus a negative 10 is the same as 7 plus a positive 10, which is 17. So I get x to the 17th. And lastly, I get y to the negative 2/3 over y to the 1/3 is y to the negative 2/3 minus 1/3 is y to the negative 3/3. Negative 3/3 is the same as negative 1. And so my intermediate step includes a negative exponent. It's bad math manners to leave a final answer with a negative exponent, so we need to rewrite that. Olivia?
How did you get the 17?
So, great question. How do I get the 17? We had an x power on top and an x power on bottom, so I can use my quotient of powers property where I subtract exponents. Top exponent minus bottom exponent. What's 7 minus a negative 10? So if it's 7 minus a negative 10, that's the same as 7 plus a positive 10 is 17. Another way to do it would be to grab onto this bottom power with a negative exponent, hop the line, and change the sign. X to the negative 10 on bottom is the same as x to the positive 10 on top. Joining x to the positive 7 for a grand total of how many x's on top? 17. So either way is worked, and you can do it either way. All right, so what is that y to the negative 1? It's 1 over y to the positive 1. My final answer is negative 3x to the 17th all over y, box it. That's supposed to be a negative 1/2 power. So a over b to the negative 1/2 is the same as b over a to the positive 1/2. And that's b to the 1/2 over a to the 1/2. And that's as far as we can go. Number 19, e to the negative 2/3. That's a 1 separate. That's the same as 1 over e to the positive 2/3. That's it. And 25, solving for x, we ask ourselves, what property, right? What property allows us to multiply powers with like bases? What do we do with the exponents when we multiply two powers together with like bases? What do we do with those exponents? Katie? Absolutely, we add them. And so figuring out what x is the same as adding 4/3 plus negative 1/6. So x must equal 4/3 plus a negative 1/6. Can we combine two fractions through addition or subtraction? Well, we can, so long as we first construct a common denominator. And so we multiply this first fraction by 2 over 2 to make a common denominator. That would give me 8/6 minus 1/6 equals 7/6. So x must equal 7/6. So x must equal 7/6. And we're 1/2 to go. I think the easiest way to do number 16 is to first do my power of a power and keep the negative and then flip last, right? But the choices are, so I'll go ahead and do 16 over here. So I'm thinking our best First step would be to raise the power to a power that's going to be m to the 2 times negative 3/4. So that would be negative 6/4. And n to the 4th raised to the negative 3/4 would be n to the negative 12/4. Which is going to reduce nicely, I think. That's the same as 1 over m to the positive 6/4, which is m to the 3/2. And 1 over n to the negative 12/4 is the same as n to the negative 1/3, so that's n cubed. So it looks like my final answer is 1 over m to the 3/2 n cubed. We can put over here. R cubed all to the negative 3/8 is r to the negative 9/8. And that's the same as 1 over r to the positive 9/8. That's as far as we can go. And ladies and gentlemen, there it is. We found it. The one we were looking for. The last one, number 24, the last one. Let's go ahead and do that. That looks like a monster, doesn't it? No problem. We'll go ahead and handle our numbers separately. So in 24, we get negative 20 divided by 4 is negative 5. X over x cubed. It looks like I have more x's on bottom. By how many? By 2, so x squared on bottom. And then lastly, let's do our quotient of powers property again. So y to the negative 1/2 over y to the negative 3/4 is the same as y to the negative 1/2 minus the negative 3/4. That's the same as negative 1/2 plus 3/4. And what's negative 1/2 plus 3/4? 2/4 is a 1/4, yeah. So my final answer is negative 5y to the 1/4. And we can verify that through subtraction. Negative 1/2 minus negative 3/4 is positive 1/4. That was a whirlwind, ladies and gentlemen. You're going to have an opportunity to practice in just a moment. Adam. Great question. So when I did my subtraction, I did top exponent minus bottom exponent. So that would be negative 1/2 minus negative 3/4. To get this, I did negative 1/2 plus 3/4. So that's negative 2/4 plus 3/4 is a positive 1/4, meaning my y will be on top. If I had gotten negative 1/4, then it would be on bottom. To the positive 1/4. Great question. All right, we'll have a chance to practice in just a minute, but first let's go ahead and complete our closure. So x to the m, all to the 1/n power, and x to the 1n, all to the nth power, both equal the same thing. Let's rewrite that as a single power without parentheses. So those are both equal to the same thing. So x to the m all to the 1/n power and x to the 1/n power all to the n both equal the same thing. What power does that equal without parentheses? Cody? Absolutely. X to the m over n. So x to the m over n is what those both equal. Good. To evaluate x to the m over n, which would be easier? Would it be easier to do x to the m to the 1 over n or x to the 1 over n to the n? So which one of these is easier and why? Olivia B?
X to the second one.
Yeah, the second one is easier. How come? Why is that easier? Adam? Yeah, it makes smaller numbers. When I did that nth root first, it chunks it down to a smaller number before raising to the numerator exponent. And we like working with smaller numbers if we have to do it non-calculating. Absolutely right, you guys. Good job. And we don't have to solve this, but we want to know what we do procedurally to solve a power equation, x to the 2/3 equals 16. What do we do algebraically to solve this? That is, how do we undo a 2/3 power and get x by itself? Go ahead and tell the class when I call on you. How are we going to undo that 2/3 power? Braden?
You do 16 to the 3/2.
Absolutely. We raise to the reciprocal exponent. So we're going to raise to the 3/2 power. We're going to raise both sides to the 3/2 power. How many solutions are there? Because I have a fractional exponent, right? We're only going to be allowed one positive answer. So there's only one solution because we have a rational exponent. You guys did a great job today, and that was a lot of stuff. We can work on assignment number 5 now. You've got about 9 minutes, so everyone can at least get going on your assignment and get the first couple done. Let's make sure you get it while you're still here in practice. And I'll go ahead and stop and save the notes. Good job today.